So today it is our continuation of the previous classes. That means the projection formulas we already started, and I will continue with some examples, few examples more due to the different types of the projection formulas that we have already studied. So few questions may be there. You may face these questions in your exams, like draw some few molecules by Shaw's projection formula, then convert it in Newman projections formula. So how do we convert them from one into another? So here is the topic, interconversions of projection formulas. So how do we interconvert from one projection formula to another? We will study today. So go for that. For example, I have taken R-glyceraldehyde to convert it from Fisher projection formula to flying wedge projection formula, or 3D presentation. So for glyceraldehyde, that CHO and CH2OH are in the plane of the paper or in the plane of the board, as already discussed. And OH and H, that horizontal bonds, those are in at the above the plane or in at the below the plane. So we have to study, we have to detect what will be that, what group will be above the plane and what group will be at the below the plane. So for that we have to, first of all, we have to detect the backbone of the molecule. By this we can predict that it is the backbone of the molecule, so that CHO and CH2OH group, both of these group are in the plane, of the same plane. So if we consider that one backbone of that molecule, see, this is the backbone where the CHO is above the plane, like that it is at the above the plane, and CH2OH I have drawn over here. So by that we can conclude that if the CH2OH is right-handed, bended towards right-handed with respect to the backbone. So if the CH2OH group is bended to the right hand side with respect to the backbone, then what will happen? That H at the horizontal line, hydrogen at the horizontal line, it is right-handed. So this hydrogen will be above the plane, and left-handed OH group linked with the horizontal line will be at the below the plane, like that. So CH2OH is right-handed, bended towards with respect to the backbone. CHO is at upward side, and contemporarily the hydrogen, which is right-handed at the horizontal line, will be upward, and the OH at the horizontal plane, which is left-handed, will be at the downward, like that. So if we view from this angle, what will we see? If we view from this here, that hydrogen will be at right-handed, OH will be at left-handed, CH will be upward side, as well as the CH2OH will be downward side. So it is tallying with that. Next case is, if we think that CH2OH is bended at left-handed side, then what will happen? Imagine that CH2OH is bended at left-hand side with respect to the backbone of that compound. So CHO will be at the same side, upward side. CH2OH, as we thought that it is bended little bit left-hand side, then the left molecule, which is at the horizontal line at the left-handed side, that will be upward or above the plane, and the right-handed hydrogen, which is at the horizontal line at the right-hand side, that will be below the plane, same as it has been shown over here. So if we again want to tally with this to the Fisher projection formula, then if we view from this way, so OH will be at left hand side. Yes, it is left hand side. Hydrogen will be at right handed side. Yes, this is at right handed side. CHO will be at upward side. Yes, it is at upward side. And the CH2OH will be at lower side. So it is at the downward side. Okay. So next is vice versa, flying wedge to Fisher projection formula. So it is, see the molecule. It is a backbone of that molecule, the vertical line over here. So the normal line, these lines are in the plane of the paper. The OH is attached with the carbon by solid wedge line. That means it is above the plane of the paper. Oh, this hydrogen is linked with what? Hashed wedge lines or broken lines. So it should be below the plane of the paper. But with respect to the backbone, the COH and CH3 is in the plane of the paper, as we have already told. So see, this CH3 is little bit painted left with respect to the backbone. So as it is left painted, so correspondingly this OH group is above the plane of the paper and hydrogen is below the plane of the paper. Next, we can go for the Fisher projection formula. If we view from this way, if we view from this angle, that OH will be left-handed side, hydrogen will be at right-handed side, as we have seen, and the COH will be upward side and the corresponding CH3 group will be at downward side. So by that way we can predict the Fisher projection formula of the same compound which was in flying wedge formula. So this way we can convert the lactic acid from flying wedge to Fisher projection formula. Our next topic is how do we convert the Fisher projection formula to Shaw's. I have taken 2,3-dibromobutane for example. In Fisher projection formula, see, there is two center carbon, first carbon, second carbon. So front carbon is linked with three molecules, bromine, hydrogen, CH3, and the back carbon is again linked with hydrogen, CH3, bromine. Okay. So how do we convert in it? Shaw's projection formula. So what is the front carbon? This was the front carbon. Draw that front carbon and link it as it is linked with bromine. So we can draw bromine in this way. Hydrogen is right-handed side. Yes, it is right-handed side. CH3 over here. So same type of structure, that three pairs and these three groups. Secondly, this carbon is linked with the back carbon. Same, this carbon is linked with the back carbon, where the left-handed hydrogen is here, same at it, and the right-handed bromine, this over here, and the CH3 is over here. So now this is eclipse conformation, as the CH3 is just back of this CH3. That CH3 is back with this CH3, bromine, hydrogen. So hydrogen is just back of the bromine. Again this CH3 and bromine, the bromine is just back with the hydrogen. So here this bromine, hydrogen and this CH3 are little bit close to each other. So there is a repulsion and energy is little bit higher. So it is called as eclipse conformation. This is not very much stable. So we can convert it to the staggered conformation, which is more stable than the eclipse conformation, as because the attached group of the carbon are far away as possible. So here, keep the hydrogen, bromine, CH3 at the same position. See, hydrogen, hydrogen, bromine, bromine and CH3, CH3. They are at the same position holding the carbon. Next, this carbon-carbon bond is single bond and it can be rotated. So, rotate it in this way so that the CH3 group with this CH3 group, that CH3 group is far away. So, if we rotate this single bond in this way so that CH3 group is coming towards upward, this CH3 group is coming to upward, so contemporarily the hydrogen will be at left-handed side and bromine will be at right-handed side, like that. Do it. CH3 upward side, hydrogen will be left-handed side and that bromine will be right-handed side, like that. So it is the staggered conformation because the CH3 is the far away as possible over here and the groups are also like that. So it is more stable than the eclipse conformation. So it is called a staggered conformation and it is the eclipse conformation. Next is our Shaw-Horst projection formula to Fischer projection formula. I have taken mesotartaric acid for example, which is drawn over here in the Shaw-Horst projection formula, and we have to convert it in Fischer projection formula. So what we'll do that? First of all, Fischer projection formula, to convert it in the Fischer projection formula, first of all we have to draw the eclipse form. So it will be little bit easier for us. So what we'll do? See, hydrogen, OH, COH are at the same position which are linked with the back carbon. This is the back carbon. They are same position as in the first example. So hydrogen, OH, COH, hydrogen, OH, CH are at the same position. So keep it intact. We will rotate these groups linked with the front carbon. So rotate as it is single bond, so it can be rotated. So keep it at the lower side. The COH group we will bring it at the lower side. So as we will bring it at the lower side, that hydrogen will be left hand side and the OH will be right hand side. So the transformation is like that. COH at the lower side, OH will be right handed side and the hydrogen will be at left handed side. So it is the eclipse conformation. Again, the COH is just back of this COH, hydrogen, hydrogen and the OH and OH. These are at the same parallel side. So from that way, we can convert now the Fischer projection from the eclipse conformation very easily. How can we? Draw the H, OH, COH. H is left-handed side, OH is right-handed side, COH is at the lower side. This is the front carbon. Now the back carbon. Again, the back carbon is linked with left-handed hydrogen, right-handed OH, left-handed hydrogen, right-handed OH and the COH. This is the COH. So by that way, we can convert the mesotartaric acid from the Shaw-Horst projection formula to Fischer projection formula. Our next thing is Shaw-Horst to Neumann projection formula. How can we do that? Already we have done with the eclipse conformation. Now we will draw the staggered conformation. We have taken this type of Shaw-Horst projection formula. What we will do? This is the front carbon, the central carbon. This is linked with CH3. Yes, this is CH3. Left-handed Cl, left-handed chlorine, right-handed H, right-handed H. This is the back carbon which is drawn as the bigger circle. Again, left-handed H. Yes, this bigger carbon is linked with hydrogen, bromine. Here it is bromine and the CH3, it is the CH3. So, we have converted the 2-bromo-3-chlorobutane from the Shaw's projection formula to the Newman projection formula, but it is staggered conformation, as it is the CH3 group and again CH3 group and another carbon. Those are 180 degree angle. These have the 180 degree angle, so they are far best away from each other. So there is no repulsion. It may be, but the lowest. Again, the chlorine and bromine, they are also far away as possible. Hydrogen are also far away as far as possible. So the repulsive force is not at all. It may be, but very little amount, and it is the most stable structure it may be. So we can draw the staggered conformation in that way. Same thing, but we have to draw it in eclipse conformation. The front carbon is hydrogen, chlorine, CH3 attached. Front carbon is hydrogen, chlorine and CH3 attached. Back carbon containing hydrogen, bromine, CH3. The bigger circle is the back carbon which is linked with hydrogen. Yes, this is hydrogen, linked with bromine, and the CH3, that red bonded CH3. So by that way we can draw the Newman projection formula in eclipse conformation. Because it is eclipse, that CH3 is parallel, very close to each other, and the repulsive force is higher, rather the staggered conformation. So it is little bit less stable than the staggered conformation. So this is your homework. Conversion, you have to convert this molecule to Fischer projection formula, this molecule to Newman projection formula. So pause the video, do it yourself, and then tally the answer. So this was your answer. How do we convert it? Tally. If we see from this way, from this angle, the OH is left-handed side, OH will be at right-handed side. Yes. CH3 will be at upward side and hydrogen will be at downward side, right? Next is this to Newman. So front carbon, consider left-handed is hydrogen, front carbon hydrogen, right-handed bromine, lower side CH3. The back carbon containing again left-handed side hydrogen. So the bigger circle one is the back carbon which is linked with hydrogen, right-handed bromine, and the upward side or just behind that CH3 is this CH3, right? So we can convert it to Newman in this way. Next, our work is this Fischer projection formula to Shaw's, then convert it to Newman. Do it yourself and tally your answer. Yes, this is our answer. So front carbon OH CH3H, OH CH3H. Back carbon is again linked with left hand hydrogen. Yes, left hand hydrogen. Right hand CH3, right hand CH3, and that OH. Yes, this is OH. Now convert it in Newman projection formula. In the same way, the front carbon, this is the front carbon linked with OH, CH3 and H. The back carbon again linked with H, CH3, OH. H, CH3, OH. But in this way, how do we convert it? We have rotate to some extent so that this hydrogen is coming over here. If it is coming over here, so OH will be tilted towards left and CH3 will be tilted little bit right. So by that way, we can get this projection formula. So thank you for today.